Hello, friends. James, thank you so much for that kind introduction. I'll assume it was a kind introduction. Thank you so much, and thanks so much for having me. I am delighted to be here to share this. Share some of our latest work with sort of a like-minded crowd. And I'm thinking that because this is kind of like an intimate setting, we could just sort of keep the talk kind of fun and interactive. If anyone has a question, I bet I'll just be able to hear you from where you are. And so, yeah, let's light this candle and don't be shy. We can do questions in line. Okay, so I'm going to start with an observation that I think we can all get excited about. Modern AI systems have achieved superhuman performance on some very challenging sequential decision-making problems lately. And what exactly do I mean by sequential decision-making problems? I mean problems where there's an agent in an environment and it needs to choose a sequence of actions to achieve some goal. And the subfield of AI that deals with this setting is called reinforcement learning. You know, not that the name really matters, but in case it comes up at a dinner party, it's fun to know about. And recent advances in reinforcement learning have led to some really high profile breakthroughs in the scientific community and beyond. And actually, just so I can kind of calibrate, raise your hands if you're familiar with reinforcement learning already. Okay, raise your hands if you actively do work in, like if you do research or build products that involve reinforcement learning. Okay, cool. So I think these slides are like calibrated roughly at the right level then. Okay, so so reinforcement learning has been kind of at the center of some really high-profile breakthroughs recently. So reinforcement learning has been applied successfully to achieve superhuman performance a few years ago on Atari games, then the board game Go, and then more recently on StarCraft 2, Texas Hold'em Poker with multiple players, and even more recently on the game of Diplomacy, which requires sort of open-ended, free-form dialogue and forming cooperative bargaining strategies with other human players. Okay, so at first glance, these applications might seem all kind of somewhat contrived, because who really cares about gambling and playing video games? But there are lots of practical real-world applications in robotics and AI that you could formulate as video games or as a form of poker or as a form of diplomacy. In other words, there are lots of applications that you could formulate as sequential decision-making problems. In fact, there's one especially exciting application that we're probably all familiar with, perhaps without even realizing it, and that's ChatGPT, which is trained using a reinforcement learning technique that incorporates human feedback to make its responses feel more natural. Okay, and also, how is my voice? Am I too loud or too quiet or just right? Perfect? Okay, cool. But if we already have such powerful tools for sequential decision-making, then it seems like we should already be able to build intelligent machines that interact with the physical world in useful ways. So why don't we all have household chore robots? Is loading the dishwasher really that much more complicated than playing StarCraft? I mean, in many ways, it should be less complicated, because I promise you that I'm way better at loading the dishwasher than I am at playing StarCraft. Okay, so one of the main reasons why, or I think one of the main reasons why we don't all have household chore robots yet, is that reinforcement learning algorithms that we have today need a lot of experience in order to learn intelligent behaviors. In other words, these algorithms are known to be really sample inefficient. They need a lot of experience to figure out how to get the results that they want, and it's just really hard to get that experience in the real world. And to see just how hard it can be to get that real world experience, here's this so-called arm farm setup that Google built a few years ago. And they needed to train all of these robot arms nonstop for a couple of months to get reasonable grasping behavior. And that was just for grasping, which is only like a small part of the overall problem of getting chores done. So yeah, running reinforcement learning algorithms in the real world, it works, but it's a huge pain. I mean, yeah, like, can you imagine like maintaining all of this infrastructure? I mean, what a nightmare. This is the robotics session. So we all work with robots, right? So just imagine all of these arms, they break all the time. You need to replace this and that. Some joint is slightly loose, so now all of the equations are slightly wrong. The MATLAB code that postdoc wrote a while ago that no one knows what it does anymore. Well, that crashes like every few hours, and then you need to reboot everything. I mean, yeah. So maintaining like such infrastructure, I think, would be quite unpleasant. And as we think through the complexity of maintaining all of this real world reinforcement learning infrastructure, there's like a critical limitation of this family of methods that kind of that becomes apparent, and that is most of the success stories out there where reinforcement learning has been applied successfully, like Go and StarCraft, are in domains where there's some kind of accurate simulator that's readily available. And that's because simulators allow agents to get a lot of experience quickly. It's possible to scale up and distribute the learning problem in the cloud relatively easily. And it's always going to be easier to launch like 100 cloud instances running a grasping simulator than it is going to be to initialize 100 real-world grasping robots. I think even the arm farm folks at Google would probably agree that in practice, large-scale reinforcement learning probably requires accurate simulation, or at least benefits very heavily from it. Okay, and immersive 3D simulators can be especially helpful for robotics applications because they can help robot agents to gain experience about the physical world in 3D. And here I'm showing one such simulator. Okay, so this is AI2 Thor from the University of Washington and the Allen Institute. And this has been enormously impactful in the research community, and it's been a huge inspiration for me ever since it came out. But I think it's fair to say that existing simulators, AI2 Thor included, have some important limitations that prevent them from being applied to some of the most fundamental real-world problems in robotics. They have limited content diversity, so they don't come with that many scenes, and each scene doesn't have many objects that the robot can interact with. And of course, you can kind of work around this by taking the scenes you have and then remixing them and trying to, generate procedural variations of your existing scenes and so on. But you're still kind of limited to the number of scenes that you have prior to remixing. And they're also limited by realism, okay, of both the rendering and the physics. It's true that this simulator is immersive, but you'd never mistake an AI2 Thor image for a real image. And so I think it's fair to say that there's a big domain gap. There's a big domain gap that remains between the real world and these existing simulators. And this makes transferring behaviors to the real world that you've learned in simulation more difficult. And then additionally, these existing simulators tend to have a lot of kind of magic actions, what I'll call magic actions, like an open door action or a closed laptop action or something like that, that don't really correspond to the action space of any real robot. And that means that these simulators can't be used to address sort of some of the most fundamental low-level dexterous manipulation problems. So one of the goals in my research group at Intel Labs is to build an interactive simulator that is suitable for household chores and other manipulation tasks that has greater content diversity and improved visual and physical realism. So for the rest of the talk, I'll be presenting the simulator that we're building called Sphere that I think is making progress towards this goal. And I should warn you that everything I'm showing is like an early work in progress, so please go easy on me. And I think there's some talks later in the day from another simulator that my group at Intel is involved in, and that's the Carla simulator. And so this is much less mature than Carla. So yeah, just a warning there. But at the same time, I think we are making meaningful progress that I think the open source community could get excited about. And so I think it's a great time to share. Okay, so Sphere consists of 300 unique scenes with over 2,000 unique rooms and over 17,000 unique objects that can be manipulated individually. And we've been working with a team of professional technical artists for several years to develop and refine these scenes. And so here's a few of the scenes that we're developing in Sphere. And we're building Sphere on top of the Unreal Engine, in particular Unreal Engine 5, which is one of the most popular game engines for AAA and indie game development, and it has a ton of next-gen graphics features. It also happens to be 100% open source, and it's free to use for research purposes. It's permissive, and it's even permissively licensed for commercial purposes. Yeah, so we like Unreal, and we're implementing our scenes here and our objects and robots as Unreal Engine assets. And as an aside, so we really like building on top of the Unreal Engine, and I'll just quickly highlight a few reasons why. Okay, so first, there's a really vibrant artist community that's already familiar with Unreal. So there's lots of online tutorials and resources out there to help us learn. Second, yeah, so it's totally open source, so we love being able to just step through the engine code in the debugger and figure out how like the internals work, which comes in handy in case something isn't well documented. Third is it's just really mature, really large scale team that's working on it, and it's just improving all the time. So for example, in the latest release of Sphere, we got like a huge boost in visual quality without really needing to change much of our code, just because a major new version of Unreal came out and included support for a bunch of like really next-gen graphics features. And so in this sense, building on top of the Unreal Engine kind of reminds me of what it was like to be doing scientific computing on GPUs in like the early 2000s, where there was some other reason other than research why the GPUs just kept getting better and better. It was because people kept buying them to like play video games. And then likewise, the Unreal Engine keeps just getting better and better for AI and robotics because these game studios keep driving the progress there. Okay, let's see. Okay, so here's a few more scenes. Okay, and here's a camera animation from our apartment test scene, and there's just like while I've got this animation going, there's just a couple of things I'd like to highlight. So first, this animation runs in real time. So on my desktop at home, this scene runs at roughly 60 FPS at around 4K resolution. And even when rendering at that high resolution, you know, the lighting, the shadows, the reflections are all quite photorealistic. Unreal does make some compromises to hit that 4K 60 FPS target, but I think it's fair to say that they're pretty hard to notice. Okay, and then the second thing I'd like to highlight is absolutely none of the visuals in this scene are pre-computed. So this scene is fully dynamic. All the objects can be moved, all the lights can be moved, you know, the time of day can be changed, all that stuff, and the rendering will respond appropriately in real time, and I'll demonstrate all of that in a few slides. Okay, and then here I'm showing the same animation while also showing some different image data modalities that you can generate in Sphere. So depth images are interesting because they mimic the observations that you'd get from a real-world depth camera, like one of the new iPhones or a Microsoft Kinect. You know, because we're running everything in simulation, our depth data is pixel perfect with no noise. And you might think that's a bug rather than a feature because, you want your household chore robot to be robust to like noisy sensor measurements. But I claim that clean depth images are still a feature because it's easy to add noise. It's so much easier to add noise than it is to remove it. It's always possible to add more noise. And then the semantic label images, that's where each pixel is colored according to what type of object it is. And that can be useful when training passive perception systems, and also when training active systems like robots. It's also useful as a debugging tool because if an agent is struggling to learn some kind of skill, then that might be because it's the agent is struggling to understand just the visual world, or it might be because the agent lacks the sort of motor skills. It might be that the agent understands the visual world perfectly, but just doesn't have the motor skills to perform the action. And so if you sort of swap out kind of the like realistic image for the semantic label image, then you can sort of tease apart what is causing an agent to struggle. Okay, and then surface normal images. That's where each pixel is colored according to how the surface is oriented. So notice like all the surfaces like the ground that are sort of flat are all the same color, and that type of image can help a robot to understand where to place objects so they won't fall. Okay, and so here I'm showing another spear scene where we're simulating just this like kind of mini earthquake, and this highlights the kind of clutter that's in our scenes, and just how many kind of like the overall density of objects in our scenes that can be manipulated individually. So nothing's like glued down or kind of attached together as one big object. There's like a ton of separate objects here. And this makes our scenes well suited for manipulation tasks and rearrangement tasks. And as an aside, this type of kind of mini earthquake simulation could be used to procedurally generate randomized initial states. That could be the sort of like initial states for kind of like a cleanup task. I mean, who hasn't had a dinner party at some point at their place and then it looked like that the next morning? Anyway, okay. So here we're showing another spear scene where we're changing the time of day to highlight just kind of how dynamic the lighting is in our scenes. This kind of visual variation can also be useful during training because, it helps a robot to sort of become robust to the visual variations that are all around us that don't change the kind of underlying meaning of the task that the robot is trying to perform. So a robot should be able to clean the house successfully, kind of no matter what time of day it is. Okay. We currently support a couple of different robot types just right out of the box today. The first is this fetch robot that has wheels and a multi-link arm and a gripper. And this robot is well suited for mobile manipulation and rearrangement tasks. Here is our fetch robot in a different scene. And in this video, we're not doing a scripted sequence of actions, but instead a colleague is driving the robot with our kind of debug keyboard interface, so the motion isn't quite as smooth as in the previous video, but I still like this demo because it highlights how kind of dynamic the lighting is. I like how the lighting is kind of responding dynamically to the motion of the robot in the scene. Okay, we also support this OpenBot agent. And we like supporting OpenBot because absolutely everything about this robot is open source, okay? So starting all the way from the physical design specs, you can 3D print everything yourself. All the hardware is all like, just the hardware and software stack is completely open source all the way down, all the way up, all the way to the perception and control algorithms that are running on board. And OpenBots are also really affordable, okay? Because the OpenBot framework uses sort of a custom app that you can install on your smartphone to do all of the kind of thinking, so all of the perception and planning and control. Using an existing smartphone for this purpose just avoids a lot of custom parts and enables users to just build like a complete working OpenBot for around $50 USD. And so that's great for doing really lightweight experiments in the real world. So in contrast, like that fetch robot is like $20,000, but you can build an OpenBot for $50. And so that's fun for doing experiments that involve transferring behaviors from simulation into the real world. But I'll talk about that more in a few slides. Okay, and then finally, I'd just like to highlight this is our latest scene that we've been working on, and this is kind of a smart warehouse type of scene. We're about to ship this fully updated for Unreal Engine 5 in our next release. And for this scene, we really tried to design it to be as functional as possible. So we drew inspiration from all those, how do Amazon fulfillment centers work? What are all the different steps of like an Amazon fulfillment center? Like all of those videos on YouTube. And we tried to sort of mimic a functional design that sort of reflects those overall steps in this scene. It's like, really big. I think it's sort of like, over a square kilometer, sort of from corner to corner. And so we're excited to ship this scene in our next release. One of the fun things about this scene is that there's like people in the scene just sort of doing their walking animations and stuff, and so it's a potentially kind of interesting scenario for robots to sort of train robots that need to kind of interact with humans and stuff like that. Okay, and while this is playing, James, I have a question for you. Do you remember what time we started? I just want to make sure that I'm on track, not doing too many anecdotes, being respectful of everyone's time. 9:20 exactly. Okay, cool. Okay, then I think I'm doing just about right on the timing. Okay, so to sort of to just try to be concrete about our contributions here. Okay, so we're not the only simulator out there that's kind of making progress towards this kind of high-level goal of supporting household chore robots. There's plenty of other simulators out there. The contribution of Sphere specifically is that we believe that we're the interactive simulator with the most unique scenes, and that's prior to remixing, and also the most unique objects. And of course, we like the sort of strategies that you could use for remixing or procedural content generation and the overall number of sort of like base scenes that you have before remixing are like complementary. So for example, like iGibson 2.0 very aggressively remixes their scenes and they generate a ton of variations. But we think that all the algorithms for generating those variations are just totally complementary to Sphere. And so we think that you could plug those same algorithms into Sphere, remix our scenes, and then have even more sort of data diversity. Okay, all of our code is publicly available today under an MIT license. And speaking of code, I just want to dive in a little just to sort of show a kind of hello world Sphere program. So it really does fit on a single slide. You can be controlling a robot and getting photorealistic observations and a reward signal. You really can be doing this in kind of like a slide's worth of Python code. And this interface will be familiar to the reinforcement learning folks in the room that have worked with the OpenAI Gym. So we've intentionally designed this interface to mimic exactly the OpenAI Gym interface, and that means that it'll just plug and play with with your favorite reinforcement learning framework out there, like RL, lib, and whatnot. And the overall idea is you sort of create this env object that kind of encapsulates the agent in the environment and the environment itself. You call reset, that sort of gives the agent its very first observation. From there, you formulate an action. So this action that we're doing here, you can think of it as like we're controlling a little OpenBot vehicle, and we are controlling the wheels with this set duty cycles action that just takes as input 2 numbers, and that tells the wheels how fast they should be spinning. This is, by the way, the exactly identical interface as it exists on a real OpenBot. So you can. So setting things up in this way supports, training in simulation and then just deploying directly without doing anything else, no modifications required whatsoever, just deploying your trained behavior on like a real world OpenBot. But anyway, so that's the action space here. You get an observation back when you call this env.step function, and then you can introspect the observation. It's just a dictionary, and it has like multiple components in there with, in this case, different modalities of images. You can get the wheel rotation speeds, all that stuff. Okay, so yeah, it's a simple Python interface, and it'll be very familiar to anyone who's worked with the OpenAI Gym. Okay, cool. So let's do a deep dive now into some applications and some experiments. So I have alluded so far in this talk to be the ability to train stuff in simulation and then deploy stuff in the real world. And so we did an experiment where we were training a point goal navigation policy entirely in simulation, and then deploying it in the real world and seeing how well it performed. And so just to kind of sketch out the high-level methodology here, and because I think this is like a kind of generally applicable and kind of interesting sort of way of leveraging simulation. So in simulation, we have access to sort of privileged information that you would not expect to have in the real world. In particular, we have access to sort of this video game-centric data structure called a nav mesh, which you can query it to say, okay, what's the shortest path, from this point in the scene to this other point, and it'll like tell you a path that is sort of navigable for your agent. That is like the most sensible way to navigate from sort of point A to point B and not hit obstacles and stuff, okay? And that's only available in simulation, of course. So we use that to generate a lot of sort of successful trajectories. So, in simulation, when we are, like during training, we will say, okay, here's my start state, here's my goal state that I'm trying to get to, query the nav mesh, figure out how to get there. Then we will execute a trajectory in simulation on the robot so that it follows that path that we got from the nav mesh. And then so now we have a goal, and we have a sequence of actions that the OpenBot took to sort of achieve that goal, and then we have a bunch of observations that were collected along the way, and that means that we have all the data that we need to sort of plug that data into. In this case, we used like an imitation learning framework. So we weren't using RL in this experiment; we were using imitation learning, and we were able to train a navigation policy by doing that. Then, once we had the trained navigation policy, then we were able to deploy it on a bunch of different OpenBots in the real world, and we set up a bunch of like sort of test episodes of point goal navigation in different members of the team in their apartments. So we and the image on the right here, this is showing like one such apartment. So training and simulation, and then because OpenBots, they're so lightweight and easy to build and stuff, we were able to just sort of build a bunch of them and then deploy these train navigation policies in different people's apartments. So here's kind of a video of just us training our doing our training and simulation. And I will say, just as a quick comment on this video, so we did this experiment a while ago, and we were still on an old version of Unreal, but so the visual quality of those synthetic images is like sort of a step down compared to where we are today. But I wanted to include it anyway because I kind of like showing the kind of progress that we've made, and that is actually the visuals that we were using when we were training this navigation policy. And then here's us deploying like, you know, the OpenBot in the real world. Okay, and then just as a sort of baseline, we also compared this to real world data that we collected by handing out a bunch of OpenBots. We handed out like, I think 50 OpenBots to just people on the internet, and then we had them collect sort of real world navigation data in their own homes. And so we have a ton of like real world data as well. I think we have like over I can't remember exactly, between like 50 and 100 hours of like real world navigation data that we could also use, and it's all paired with like, you know, the actions that the person was doing and the observations that they got at that time and stuff. So it's like the exact same sort of format of data, and so we were able to use that as a data source to train a navigation policy as well. And so we were able to do this kind of head-to-head comparison of sort of training with real data and training with synthetic data. And what we found, and this like really surprised us. I thought this result was really exciting. So we found that training with enough synthetic data actually outperformed training with all the real data. Okay. And how could that possibly be? Because there is still a domain gap. And I mean, if you like look at this video, I mean, yeah, this is Unreal Engine 4. Our stuff looks way better now, and there is a kind of decently large domain gap between these videos and the real world. So how could this possibly be? How could training with synthetic data outperform the real data? And it's because it's just really hard to get humans to provide like awesome examples, like awesome example trajectories that are like exactly optimal for the situation. So while there is no, in the real data, there is no domain gap to worry about whatsoever. It's real data, so no domain gap. But there is there's a significant optimality gap with what the user is actually doing versus what would be optimal in that situation. And we found that it's a really harmful effect when training. So the synthetic data ends up being the sort of lesser of two evils in this case, where there is a visual domain gap, but there's not such an optimality gap because we're using that privileged information from the simulator so that at least the robot is sort of doing approximately the optimal thing in that situation. And we found that at least in this experiment for point goal navigation, doing the optimal thing with sort of imperfect like synthetic data is better than doing the like very clearly suboptimal human thing, but with like perfect data. And so we thought that was interesting. And of course, you know, so that is, it's already hard for humans to do the optimal thing with an OpenBot, which is like, I mean, driving an OpenBot, it's basically like playing Mario Kart. It's like, it's not that hard. And so like controlling a multi-link, I mean, everything beyond OpenBot, it just gets harder for humans from there. So like, I expect this gap to sort of widen as you move to sort of more complicated robot systems. I don't expect it to narrow because more complicated systems are it's just hard. It gets harder and harder for humans to do the optimal thing. Okay. We also used our data on a purely passive perception task. So we trained a semantic segmentation model on, you know, where we were like pre-training it on our synthetic data, fine-tuning it on some real-world data, and then evaluating on real-world data. We found that SPEAR data leads to better downstream performance on that semantic segmentation task. And this is like a hint that there's just sort of like less of a domain gap than there is with like existing simulators. And that was for SPEAR before we moved to Unreal Engine 5. So I expect that if we redid this experiment today, then we would see an even more pronounced gap where the outperformance of SPEAR would be even more pronounced. Okay, we also, because there's different ways that you could evaluate photorealism. One way is to sort of evaluate on these downstream perception tasks. Another way is just to ask humans what they prefer. So we asked a bunch of humans in a mechanical Turk experiment, which image is more realistic, A or B, and we found that humans prefer SPEAR. Between sort of like in the 60% of the time. So, definitely there's no danger here of SPEAR sort of being like in a 50-50 tie with any of these other simulators. It's clear that humans think that SPEAR images are more realistic. And again, we did this with old SPEAR images. So if we redid this today with like our Unreal Engine 5 images, I think the results would be more pronounced here as well. And finally, you could argue that the best way to sort of analyze photorealism is to not ask humans, but instead to ask some kind of pre-trained perception model which image is more photorealistic. And that's because SPEAR images, the whole point is for them to ultimately be consumed by some kind of AI system, not by humans. We do not expect humans to be consuming most of the SPEAR images. I think just by volume, I expect AI systems to be consuming most of SPEAR images. So you could sort of evaluate this question of photorealism in a different way, because you could take some kind of pre-trained perception model and then ask the pre-trained perception model, okay, what is the feature space distance in that induced feature space induced by the pre-trained model? Okay, what's the feature space distance between sort of all of these synthetic images coming from SPEAR and all of these real images coming from some kind of like real world indoor data set? So in this case, we used Real Estate 10K, which is like this, nice images of indoor environments. And it turns out that the sort of in that feature space induced by a pre-trained perception model, the SPEAR images, that cloud of sort of points in that feature space is somehow like more aligned with Real Estate 10K than a cloud of sort of points coming from these other existing simulators. So we measured kind of feature space distance using these like FID and KID scores. I won't bore you with the details there, but it's just a way, they're different complementary measures of measuring feature space distance. So we found that according to this feature space distance kind of criteria, SPEAR was sort of more photorealistic than existing simulators in that sense as well. Okay, so what's next for us? So we are very happy with the existing physics simulation functionality that just comes natively with Unreal Engine 5. However, for really hardcore like robotics applications where you're dealing with a lot of contact, a lot of complicated like joints and hard constraints, these like really dexterous manipulation tasks, we think that MuJoCo is really the last word for physical simulation fidelity. And so we are well underway in an effort to integrate the MuJoCo physics engine as well. We think that this will be a sort of exciting step for the robotics community. So I think MuJoCo is basically like the kind of gold standard in the robotics community. A lot of labs have their kind of robots that they work on already implemented as MuJoCo models. And if you ask robotics people, kind of what they, like how they work with MuJoCo, they'll, at least in my experience, tell you stuff like, yeah, we can basically, like MuJoCo has got to the point where if we can get our sort of problem working in MuJoCo, then we are pretty confident that it'll just straight up work on our actual robot. So that's kind of like, for a lot of robotics labs, that's how they work. Like if you have like, you know, an intern that you don't totally trust yet, then you can sort of get them to like get their code working in MuJoCo, and then that's when you can sort of like safely you know, give it a try on the real thing. So a lot of robotics labs already are working with MuJoCo, but there has sort of not historically been any kind of way of getting, you know, really like, you know, photorealistic visuals into MuJoCo. And we think that with this integration effort, we will be able to sort of combine the best of both worlds. So have that like really state-of-the-art, really nice visuals coming from the Spear scenes, but then with like, you know, really high-quality physics coming from MuJoCo. Okay, and here's like a first kind of initial glimpse of that. So this is just one of those scenes that I was showing before. This is the scene that had that like smooth time of day shift. And we have just got this working recently where we were able to sort of like import it into MuJoCo, and then there's, you know, like a robot in there, and we're just flinging things around. Okay, so you know, this is, just think of this as like the cherry on top. This is obviously work in progress kind of stuff, so, you know, like go easy on me here. But this is just showing that like we have achieved some kind of interoperability here, where we're like able to sort of get our scenes into a form that they can be consumed in MuJoCo. Okay, and then of course, you know, and then you're not done yet at this point. You still need to communicate all these state updates back to Unreal, but we think we have a good handle on that. And so, yeah, we think we'll have something to show in our next release, which will be in Q4 of this year. Okay, so, and then just sort of going beyond that, we're excited to just integrate more tasks, more sensors, and more learning algorithms into, you know, to just sort of like build out our stack to be kind of like a one-stop shop for all the kind of learning that you'd want to do to enable household chore robots. We're excited to make our control interface even more sort of fully featured with even, I mean, because, okay, so the sky is really the limit with all of the stuff that you can do in the Unreal Engine. And so we're excited to expose more and more of that via Python. And then we are also excited about eventually getting to a point where we're having kind of simulation, part of the simulation running in MuJoCo for the really high fidelity stuff that you care about, and then part of this, all the rest of the stuff, like the kind of all the background simulation stuff happening in Unreal that's happening at slightly lower fidelity. But of course the devil's in the details there, because how do you hand off, like, you know, a force or a torque that's being applied in MuJoCo? How do you make sure that it's doing the right thing in Unreal and vice versa? So we're working on, we're excited to sort of make progress on co-simulation. Okay, and then, yeah, just to kind of like wrap up here with some takeaways. So Spear, the thing that I was presenting the whole time, is this photorealistic simulator for embodied AI research. We have what I think is what I consider to be state-of-the-art rendering today, and we'll also have state-of-the-art physics simulation in the next release. We have this growing library of high-quality scenes and other art assets, and we have just 100% cross-platform open-source software stack. And just sort of zooming out beyond Spear, I really think that now is the time for photorealistic simulation. Okay, in the computer vision community, even in the sort of passive perception like computer vision community, I think people are starting to come around to the idea that synthetic data and working in simulation can be a productive way forward, but in the passive perception computer vision community, you have a choice most of the time. You can choose to work with synthetic data or not. I think that for these problems that we want to solve now that involve sequential decision making in the real world, I really don't think we have a choice. I think learning stuff like that, the stuff like household chores or navigation or manipulating objects, rearrangement, creating digital twins, that kind of thing. I just think learning in the real world is just too slow and too painful. And I think, so I think that choice that is available to you as a person in the sort of passive perception community, I don't think is available to you in the same way in the kind of active decision-making part of our field. And so, I really do think now is the time for photorealistic simulation for these kind of sequential decision-making problems. Don't take my word for it, though. We can, for inspiration, we can look to the cover of Nature from just a couple of days ago. Okay, so this result is hot off the press from 2 weeks ago, where there's yet another sort of high-profile reinforcement learning success story, where now people are using reinforcement learning to achieve world champion level performance on drone racing. And you guessed it, they trained this whole thing in simulation. Don't take my word for it. Take this group who's now doing world championship level drone racing with a combination of reinforcement learning and training and simulation. And so, I think if we keep at it, hopefully we will get to world champion level household chore robots in the near future as well. I think the revolution will not be supervised with real data. That's my talk. Thank you so much.